so it'll be posted.
All right.
So, all right. So when we're looking at the drug example here, the idea is that we've been prescribed a medicine from the doctor, and we're told to take this every 8 hours. And so we get the drug, and it's 100 milligrams or whatever. And the problem is that when we start taking this drug, when we take a pill, we don't absorb all of it. All right. So the dosage might be 100 milligrams, but our body doesn't actually absorb all of it. So that's where that absorption factor comes from. So we only absorb part of it. And so when we start taking the drug, we're going to start with that dosage. And so I'm going to do an example here where we just take the drug once. And then what's going to happen then is we get the drug in our system, but then our body then eliminates that in there. So if we look at the code that I have over here, our dosage was 100 milligrams. But if you look at the values that were given, we have the minimum effective concentration and the maximum therapeutic concentration, and those are given in micrograms. Okay, so you got to pay attention to the units that are in the system when you're, any system that you're working with. You got to pay attention to the units and make sure that when you start multiplying or dividing, you match the units. That's very important. So our minimum effective and maximum therapeutic concentrations were given in micrograms per milliliter. And so the volume is given in milliliters. So we've got the milliliters. That's good. But the drug, when you go to the drugstore, you don't buy drugs in micrograms. They give them to you typically in like milligrams, 10 milligrams or 100 milligrams, something like that. So the drug is given to us, I believe, in the book. I don't have the book with me, but I believe the book gives it to us in 100 milligrams. So we have to scale it to micrograms. So that's why I'm multiplying it by 1,000. And then the absorption factor was given to be 12%. So this is saying that out of the 100 milligrams or 100,000 micrograms of drug that we put into our system, only 12% of that actually gets absorbed into our body. The rest of it is just, doesn't actually make it through into the body. So and then we have the elimination constant is the value that is the amount that is going to be removed. And that, again, that's given in the problem there. We're given the half-life, which is 22 hours. Okay. And the log of 1/2, the log of 1/2 comes there as the half-life. Okay. And so if we just are going to take this drug once, all right. So if we're just going to take the drug once, then what's going to happen is I'm going to create a what did I call it here? I'm going to create a variable called entering. I used in the slides, I used pulse. We could call this pulse if you want. I don't care. We're going to have the pulse, and the pulse is going to be zeros, the size of my t vector. Okay, so this is going to be my forcing function. where I'm going to, in this case, it's for when I take a dose. So when I take a dose of medicine. Okay. So this is an outside factor where I'm taking, the drug is in the pill bottle. I take it out of the pill bottle. I put it in my mouth. I, get a swallow of water and I swallow this. All right. So that's the outside coming into the system. Okay. So if my body is the system, this drug is coming from the outside of the system. So that's kind of this forcing function piece. Okay. So, but right now the pulse is all zeros. And so if we look and if I run this simulation now, so this is my pulse here. Okay. And so we're going to, I'm calculating the elimination. Okay. The elimination is the elimination constant times how much drug is currently in my body. All right. So currently I haven't taken a pill yet. So I have no drug in my system. Okay. I just went to the pharmacy and I got the pills. There they are. They're sitting on the counter, but they're not in my system. So there's no drug in my system. And so the concentration of the drug within my, concentration is a measurement per milliliter of your body, of your volume. So it's basically saying, if this drug was evenly distributed throughout your entire body, how much is in your little finger? How much is in your thumb? Right? That's the concentration. So the drug in the system just says, hey, I've got, 1,000 micrograms or, 50 micrograms or whatever. So the drug in the system is just in grams or micrograms, how much I have in my body, but the concentration then is based on the volume. So what I'm doing here is I'm going to determine how much is being removed from my body, which is just the elimination constant times the drug in the system. So if we look at this, that's this over here. We have the elimination constant, which includes the half-life of the drug, how long the drug before, because the drug just starts breaking down when it's in your body anyhow. So that's the half-life. And then, so that's part of the elimination constant. The other part of the elimination constant comes from the fact that your body, your liver, is trying to pull out that drug because it sees it as a foreign substance. And so, so those are the two parts of the drug in your system, and how they get removed. Okay. And so that's what we're doing up here. We've got the, the elimination constant, which is the half-life and the, being removed from your system. And so now, if I run the simulation, okay, this is going to calculate how much is being eliminated. And then, so how much I have in my body at any one time this is my derivative, or actually, yeah, this is the derivative. This is how much drug is in my body due to how much was there before, plus how much I just put in, minus the elimination. So actually this is, so we're not even actually truly integrating here. We're just calculating how much is in the body by how much our body is removing and how much we're injecting into our body. Well, right now, if you look at this, I start with no drug in my body, and my pulse of how much I'm taking is also zero. So if I run this simulation, it's going to be all zeros. Okay. So you see it's actually down here, the blue line down here at the bottom, which is just right at the 0 line. So it's almost invisible along the black because I don't have any drug in my body. So there's no drug in my body because I started with no drug in the body and I didn't add any. So now if we look at my pulse variable here, then it's all zeros. Okay, the pulse is all zeros. This says that I've never taken the drug. I'm not taking it now. For all this time, this is 168 hours, so for an entire week, I have not taken this drug, and I didn't have any at the beginning. I didn't have any of the drug in my body at the beginning, so I've added none. So of course I have none. So it's all zeros. So what do we need to do is we need to add the pulse. So what I'm going to do is I'm going to put a pulse here when I first start the simulation at time t equals 0. I'm going to say I'm going to take one drug. So if I just do pulse 1 is equal to 1, then that says that my pulse, what I'm calling a pulse here is the taking of the drug. And so the pulse is a 1. Now, but what we have to do is we have to multiply that times the size of the dosage. So if we come back over here and we look at our dosage, all right, our dosage is equal to, or our dosage, I already have a dosage. The dosage is 100,000 micrograms. All right, so my dose at any one time is equal to the pulse times the dosage. Okay, so if we look at this now, in my pulse, I need to set the very first one equal to a 1. All right, and so now I'm going to simulate this. And I forgot to change the pulse bit here. This should be my dose. Okay, so what I'm doing, the amount of drug in my system is equal to the dose, which is equal to that pulse times the actual amount of dosage. So I took that one pill. So the pulse is the act of me taking the pill, and the dose is basically the amount of the pill. All right. So if I had to take like 2 of these pills, right, then I would have like 2 times the dosage, something along those lines. So if I run this simulation now, you see that I took the drug and I get this huge spike, and then it drops off because after I took the drug, my body starts eliminating the drug and it just decays down to 0 now. Okay, because I only took the drug once. I took the drug right here at time t equals 0, so I had this huge spike of the drug in my system, and then it decayed. Now notice it went way over. This dose went way over the maximum therapeutic concentration, right? Or the minimum toxic concentration, whichever you want to call that one. All right, so I got way too much of this drug. Well, the problem is actually I forgot about the absorption factor. So remember that even though my dosage was 100,000 micrograms, my body didn't actually absorb it. So I also have to multiply this times the absorption factor. Okay. So now if I run it, you'll see that it never gets anywhere. I do get this huge spike and then it decays off, but it doesn't get me into the danger area up here above the maximum therapeutic concentration because my body didn't actually absorb but 12% of it. Okay, so, but that's with a single pulse. So if we just look, come over to, use your command window. Okay, if you come over to your command window and you can run the who's command, and you can look at the size of vectors and things, right? And you don't want to look at them all a lot of times. So I want to look at, say, my dose, and I want to look at the pulse, and I want to look at my T, and maybe my concentration. I'm going to spell it out. I'll just put a star there. But if we do a who's with an S, right, it shows you that the concentration here, apparently I've got a misspelling. So it shows me the misspelling there too because I put the star there. So I got concentration without an R. I never noticed that. I can come in here and find that and correct that. Concentration. Okay, so then concentration. All right, so I'm going to rerun this, come to my command window and rerun the who command, see if I fixed that. Do I have a clear? Okay, so always start by clearing out all your variables. Okay. And see if I got all of them in there. Okay, but yeah, so use your window there, your command window, to look at your things, and then look at the pulse. So I'm going to look at the pulse, and you see that right now, right, I just have a pulse right at the very beginning. And then I'm going to look at the dosage. And remember, the dosage is 12% of 100,000. Not the dosage, but the dose, sorry. And so if you look at the very first value of the dose, right, it's at 12,000 micrograms. Okay, so that's how much I've actually absorbed. Okay, so the dose was 100,000 micrograms, but I only absorbed 12% of that. Okay, but those values were given at the beginning of the problem. That's where I got that 12% and stuff. All right, so now, though, what I need, though, is the doctor didn't tell me to take it once and quit, which is what I'm doing here. The doctor said take it every 8 hours. So what I'm going to do is I'm going to take my pulse vector. I'm going to take this pulse vector here. And what I want to do is I created this pulse with all zeros, the size of my T vector. And now what I want to do is I want to, if we look at T is once an hour. Okay, so T is actually nice even numbers right now. It's once an hour. So what I'm going to do is I'm going to get my modulus for every 8 hours. I'm going to use the modulus function, which is going to do a remainder, which is going to take T divided by 8. And so what you can see is it's basically gives me a result from 0 to 7, 0 to 7, 0 to 7, because what it's doing is it's just counting up basically for 8 hours, starting at 0, so I take the pill, then I go 1, 2, 3, 4, 5, 6, 7. Now I take the pill again. That's after 8 hours, I take the pill at 8 hours. And then 1, 2, 3, 4, 5, 6, 7 hours. And the 8th hour, I am going to take the pill again. So every 8 hours, I need to take the pill. So now I'm going to use the find command to find those indexes. So I'm going to say find mod 8 where it's equal to 0. and I find out that at the first value, at the 9th value, at the 17th value, at the 25th value, at the 33rd value, those are the times when this vector here have zeros in it, okay? So now notice here, this is like, you know, if you think about, we have 8, after 8 is 24, or excuse me, yeah, I can't. After 8 is 16, 24, 32. But remember, we start counting at 0. And so you see that, you know, we do it at the first time, which was at 0. And then we do it at the 9th, right? So these, we're just doing it every 8, 16, every multiple of 8. Okay, so the modulus function has given us the multiple here, a multiple of 8. But since my t vector starts at 0, we've got to add 1 extra to it. So instead of it actually being 8, 16, 24, 32, and 40 and so on, it's 1, 9, 17, 25. It gets 1 more added to it. Okay. But the modulus function is a nice way to get these nice even pulses in here. So now I've got the mod function and the index function here. And then what I'm going to do is I'm going to build up my pulse now. My pulse at these indexes is equal to a 1. And so at 1, 9, 17, 25, 33, and so on, every multiple of 8, I have a 1. The rest of the time, I'm not taking the drug, so there's zeros. And these are the inputs. This is going to be my input into the system at every 8 hours. So, you know, like clockwork, every 8 hours, I'm going to take another dose. So we need to put that into our code now. So the pulse, what we're going to do here is we're going to do mod 8 is equal to the modulus of the t divided by 8. Okay. And then we're going to say, give me the indexes where mod 8 is equal to 0. So those are the every 8 hours. The indexes at every 8 hours. So then my pulse now, I'm at the indexes, I'm going to stick in a 1, and then that is going to be multiplied times the dosage of 100 micrograms times the absorption factor of 12%. And then that is going to be the dose that I'm injecting in. So as we go through the for loop, when we hit a point that the pulse is a 1, then the dose is going to be 12,000 micrograms. And so I'm going to get a spike of medicine in my system every time that happens. And so when we plot that, then we come up with this graph. So you see it going up. That was the 12% of dosage in my body. But after 8 hours, my body has eliminated some of that. So it decreased. So now we're down here to this bit right down here. And then we get another spike of 12,000 micrograms. And so it jumps up, but then it drops back down. And then it jumps up and then drops back down and jumps up and it drops back down. And then at this point here now, it's above the minimum effective concentration, MEC. right? So, and it stays above that. So I keep that amount of drug in my body, but I'm not going above the maximum amount. Okay. So let's see what happens if I was to take double the dosage. I could come over here now and I could double my dosage and I could take 2 of these. All right. And so if I take of them, you see that, whoa, I'm way over the maximum therapeutic concentration up into the toxic concentration. So, so that's way too much. All right. But if I take, if let's say I wanted to take it, instead of taking 2 pills every 8 hours, let's say I drop down and take 2 pills every 12 hours and see what happens. So now we can simulate that, and you can see that, yeah, that's still, a little high. Maybe if I take it every 12 hours, but I only take 1.5 every 12 hours. And then I hit there. So I'm going to, instead of doing 2 pills, I'm going to do 1.5 pills. All right. And so you can see that, hey, wait, if I take it every 12 hours, if I take 1.5 pills every 12 hours, I'm still in the good. Okay. So I'm not, I'm staying above the minimum effective concentration, but I haven't reached that maximum therapeutic, getting into the point where it becomes toxic to my body. All right. And so again, the idea with these simulations is we can now, once we get the simulation working, we can come in here and we can play with these numbers and try different dosages and see where we're at and things like that. All right. So that's the drug problem. This is kind of what your plot should look like. This one was actually for the 12 hours at 1.5 pills each time. So if I drop it back to 1 pill and I drop it back to 8 hours, which is the plot that they give you, I mean, it's in your book, this is what your plot should look like. Any questions about that? You guys good with that? Okay. Thanks, Ann. All right. So what I wanted to kind of concentrate on today was, if we go to the, see, I need to back up a directory here. Oh, shoot. Went back too far. All right, so what I wanted to do was this rabbit and fox, this predator-prey model. And I've got so many of these here now, I don't remember which one's which here, but let me try this one and see what it looks like. All right. Okay, so this right here is the plot that I asked you to do for the rabbit and fox problem. And so what we're looking at here is the population of rabbits and foxes versus time, right? So our unit down here at the bottom is time. And our population over here on the independent or the dependent axis, y-axis, is in population in thousands. All right, so this should be like 2 here was like 2,000. And this system, the population of the rabbits is directly dependent on the foxes because the fox, of course, uses the rabbit as a food source. So if we look at the red here, as the red starts getting high, there's lots and lots of foxes, lots of hungry foxes, and so the rabbits are in trouble and their population starts decreasing. And so their population is decreasing very, very quickly because there's so many foxes. But as the population of the foxes decreases, the population of the or of the rabbits decreases, the population of the foxes also starts decreasing because it's harder for them to find the food. And so this is a cyclic system here. It goes up, reaches some kind of maximum, drops down, reaches some kind of minimum, and then goes back and forth. Okay. So, but this is versus time. We've plotted this versus time, which is what we've been doing all semester long so far. But what becomes interesting now is what happens if you plot the number of rabbits versus the number of foxes. And so now we get this kind of egg-shaped plot going on here where we have the population of the rabbits is ranging, we're plotting rabbits as our independent variable on the horizontal axis here. And so we see as the population of the rabbits increases, then we can see that the population of the foxes start increasing. And as the population of the foxes gets larger and larger, then the population of the rabbits starts decreasing. But we get this kind of circular sort of shape or egg shape going on here. All right. And this is what we refer to as a limit cycle because it's not just a fixed point, it's varies. You know, it's a constantly moving population. So we've got the population of the rabbits, we've got the population of the foxes, and both of these populations is constantly moving. But they're dependent on each other. And so as we run this simulation, you know, we can kind of see this. Now, the problem with this picture as we're looking at it is it's kind of hard to tell whether it's moving in a clockwise or counterclockwise manner. Okay. So if we look at this system, right? So here's our plot versus time. And so we're plotting this. This is referred to as a phase plot or phase plane. All right. And we're plotting one variable versus another. In this case, rabbits versus foxes. And so we get this limit cycle. Now, these limit cycles, they can be stable, which is what we have here. This is a stable system. You know, it's unchanging as long as we don't have any outside forces. It's unchanging, but we can, you can get stable systems here or unstable. So if you look at like this middle plot here, the middle plot is what we call unstable, where the system kind of starts here, but it's kind of like Dorothy and the Yellow Brick Road, if you've ever watched Wizard of Oz, right? They start in a circle and they start going around and around and they keep spiraling out until they're, you know, out in the forest somewhere, right? And, you know, they never seem to make it back. Okay. Eventually, Dorothy did make it back with her ruby slippers, but, you know, it was in this system here, in an unstable system, you just never make it back. With a stable system, like the left one over here, you are you're stable, but you're not constant. So you're constantly changing, but you're going around in sort of a circular sort of motion. All right, so it's stable but moving. And then if you look at the one at the right, there it's like we start somewhere. Where we start, could be anywhere, but eventually we're going to end up at a fixed point. And we're coming into this fixed point here. So no matter where we start, we're going to come into the fixed point. And there's some more there. I have a link there. You can go look at some other of these stability plots, all right? So, but one of the things we can do, because like, again, when you look at this phase plane, it's kind of a cool graph. It shows you what's happening, but it's not it's not apparent by just looking at it to tell, you know, which way the system is flowing, what motion. We kind of know the system is moving because it's a big circle, so the system's constantly moving. But what direction are we moving in? And so what we can do is create what's called a vector field. Now remember that derivatives give you the rate of change. And so basically what we want to do is when we look at this plot, I want to take the derivative. I'm going to take the derivative at this point right here. And then I'm going to take the derivative at this point. And I'm going to take the derivative at this point. And I'm going to take the derivative at this point. And I'm going to take the derivative over here. And I'm going to take the derivative over here. And I'm going to take the derivative over here. And I'm going to take the derivative all over the place for this plot. Now the system, the true system, the population of the rabbits and the foxes only exist where the blue line is at. But all these other points here, all these other points along here, you know, if you started here, if your population started here, where is it going to move to? Is it going to move up and over? You know, if I start like over here at this point, is my population going to move this way, or is it going to move and then around this way? And so if we look at the derivatives at these points, even though our population isn't technically at these points, but if we look at this point right here, so look at this point, the population of the rabbits is 5, and the population of foxes is 1. So right here we have a rabbits is 5, and the foxes is 1. So at this point here, let me shrink that text down a little bit. It's really big. Okay, so right here at that point, at this point right here, right, we're at foxes 1, rabbits 5. If that was my current population, how am I going to move? What direction am I going to move? So if I take the derivative, of that, it will show me the not only the rate of change but the direction, because I'm going to get the x and the y directions there. So what we need to do is we need to come up with a way to get all these points in here. So we have to go and take all these points on this as a grid and take and get all kinds of points here. And then we can plot what's called a vector field. And so now you see these arrows. Okay, this is the vector field, and it's showing you the direction of flow, and it also is kind of showing you the strength. By the size of the arrows, it's showing you that it's a big heavy flow, or maybe the flow is slowing down. So the smaller arrows here, like especially down here in the lower left corner, you know, it's not moving very fast because the population of both the rabbits and the foxes are really small, and so the change is very slow. Okay, and like down here you can see that the population of the foxes is really slow all along the bottom, is a low population of foxes. And so as the rabbits start growing, they start growing faster and faster and faster. You can tell that by how big the arrows are getting, right? And then as the fox population begins to grow, it kind of shifts around. But this vector field shows us the flow of the limit cycle. All right, so how do we do that? It's actually quite easy. What you do is you use this function called a mesh grid. And the mesh grid is just going to give you an array of points all along here. So when you look at this, at every one of these arrows, you're looking at the beginning of the arrow, at the base of the arrow here. Okay, right here at the base of the arrow, you're looking at this point right here, and you're taking the derivative in both the x and the y direction and calculating how fast you're changing in the x direction, how fast you're changing in the y direction. Okay, and so we build up the mesh grid using the linspace. Now, one thing I've experimented with this, and I find that when you set this up, right, you got to look at your original plot and look at your units. So here we're going from 0 to about 1.2 in the y, and about 0 to 6. Right, so we're going from, in the y, we're going from 0 to about 1.2, and in the rabbit population, we're going from 0 to about 6 over here. So that is our range that we want, and we want to basically just take a whole bunch of points in between here in both directions. So for every one of these arrows, we're picking a point. So like this point right here, this is at like 0 and about 0.05. Or excuse me, this is one rabbit or 1,000 rabbits, because the units are thousands. So we're at 1 and 0.05. And this point here, we're at 1 and 2, or it looks actually maybe a little bit more than 2. But we're just going to pick a whole bunch of points all along here. So all along here for x, all these along here, the y value is at like about 0.05. So the y value is at 0.05, but the x value is changing from about, 1/3, 2/3 to 1, 1 and 2/3, 1 and 1 1/3, 1 and 2/3, 2, and so on. So we're just picking points all along inside of this graph here. So the way we do that is we're going to use the mesh grid function, and we're going to I'm using the minimum value of rabbits and the maximum value of rabbits to find my range, and I'm just going to say give me 20 in the x direction in terms of rabbits, and give me 20 points in the y direction for the foxes. And what this does when you do this mesh grid is it just gives you a whole bunch of points, x comma y. If you think of the graph as being x is the horizontal and y is the vertical, you're just getting all points along there. And you're getting 20 points from the minimum value to the maximum value. And then once you do that, then you take this derivative. Remember that the change in rabbits was equal to that constant times the rabbits. But now instead of using the rabbit value, I'm using the result of this mesh grid. And so I've got my rabbits xx minus b times rxx, rabbits xx. And then you got to use this dot star notation again. And then foxes, which is in the y direction. So you take and evaluate the derivatives for each one of these points in your grid. So you get your rabbit, the change in the direction, the change in the amount of rabbits, and you get the change in the amount of foxes. And so at these points, then you plot the change in rabbits versus the change in that using what's called the quiver function, which is what draws the arrows. Okay. And one thing when you do this, sometimes you got to tweak it a little bit to get a nice graph. And so you can mess with like the size of the arrows. And I got several examples in here. But you can change the size of the arrows by capturing your settings, or your handle to your quiver. And then you can use the set command. Now I've got it commented out right here, but it's something you can experiment with, changing the size of your arrowheads. Other things that we can do when we're doing this is we can change how many. So you see like here in the X direction, I did 100 values, or excuse me, this was actually in the Y direction. In the Y direction, I did 100 in the Y direction, but I did 20 in the X. And when you look at this, you see this plot isn't really all that good. All right. And so then here, I actually reduced it down to 5 to kind of just show you there. Here I did 20 by 20. And so you can just kind of see, somewhere between about 20 to 40 seems to usually give you a good number, but you may have to experiment a little bit with this to see a good plot. Okay, so you have to do it a few times. So here is a plot with the vector field being 20 by 20. And here is a plot where I've got 34 by 40. And I think both of these are pretty decent, but this one kind of has pretty large arrows, especially over here, like on the right-hand side. This one here, 34 by 40, maybe I think is a little bit better. Okay, so you can, run it a few times and until you get a nice looking plot. All right. Some other things that we can do when we're doing these plots is we can set a start and end point. Okay, since we're not plotting versus time here, it's sometimes hard to tell where we started and where we ended. So in this case, what I did was at my first point, I made that a big green mark there. So you see the plot X parentheses 1 comma Y parentheses 1, X parentheses 1, Y parentheses 1. I'm plotting a green asterisk. So I just at this one point, I'm just putting a green asterisk there as a marker, showing you this is where I started. And then at my ending value, I'm plotting a red one. All right. And then you can also use the marker side option to increase the size of those, because if you don't, they're there, but they may not be real huge. And so if you increase the marker size, you can make them a little more visible. Okay. We can also do three-dimensional plots. So in this case, we're kind of simulating a two-dimensional robotic arm. So it's moving in the X direction and the Y direction, and it's moving over time. So the green, again, I put the green start point here. So this is where we started. And then you can kind of see that the arm kind of traversed and moved here and there, and it ended up over at the red dot. Okay. So notice that the independent axis here is actually time in this case. So I'm only plotting in 2D, but I'm plotting versus time. So that's my time is kind of my third dimension in this case. All right, so I just kind of show that a little bit, zoom in on that picture a little bit and marked out the time. So time is moving this way, and so we have X going horizontally and Y is going vertically there. But so this is movement in time. This arm is just going to move along here. So when you have multiple dimensions, you can plot versus time. So you could actually plot that in 3D. So it might be kind of interesting to come back to our rabbit plot. I might try doing this, plot our rabbit population and our fox population versus time. So we can kind of see that move. Okay. One other thing we're going to be doing here is we're going to be plotting some higher order systems. Okay, so far our systems have kind of been smaller, but what we're one of the systems we're going to simulate is the weather system. We're going to try to simulate the weather, and it turns out that any nonlinear differential equation of order 3 can go into what they call a chaotic system. So if you look at this is a plot here of a third order nonlinear system. All right. So for a system to go chaotic, what does that mean? Well, the system is deterministic, which means that we can determine how the system is going to behave. But the problem with chaotic systems is that even though they are deterministic, that we can determine how they're going to change with time, they turn out to be very, very what's the term? Their initial condition has a dramatic effect on them. All right, you may have heard this referred to sometimes as the butterfly effect. You know, so like if a butterfly in South Africa flaps its wings, it makes it rain in Central Park in New York City. Something like that. That comes from the Jurassic Park movie. If you ever saw the original Jurassic Park movie, he talks about the chaotic system and uses that example there. But the idea is that just a very slight change in an initial condition or a very slight disturbance in the system, even after the initial condition, can change the behavior of the system because it's nonlinear and it's a chaotic system. So most of the stuff that you ended up doing in your like calculus class when you're solving those equations, a lot of that stuff was nice linear systems. And linear systems are very easy to understand and easy to simulate and easy to predict. But one of the most common chaotic systems that we here in Ohio are definitely aware of is the weather, right? And so we're going to look at the Lorenz equation. I actually have a link out there in Blackboard of a video that was done. I think it was a PBS video, and it shows shows them simulating the Lorenz equations to simulate the weather using what's actually called an analog computer. So when you see if you watch that video and you see it was done a long time ago, and they're actually doing it on a analog computer, not the digital computers that we're using, but an analog computer, which but it's simulating that. And of course, like I say, we know the weather is extremely chaotic. But when you program it, the programming is basically still the same. you set your initial conditions. Where's my program here? You just set your initial conditions. Okay. Well, again, you should start at the top by clearing all your variables and graphs. Then you and define your time step, your time vector, and initialize all your variables and your scalars, your coefficients, initialize everything. And then you do the for loop. Inside the for loop, you do your evaluation of your derivative, just like we were doing with the population of the rabbits and the foxes or whatever, and then we integrate to calculate the new value. So it really doesn't matter whether the system is nonlinear or linear. If we're doing it using Euler's method, it's the exact same method. Define your time step, build your time vector, initialize all your variables, including your initial values of your process variables there, your rabbits and your foxes or whatever it is that you're simulating. And then do your for loop and evaluate derivative or derivatives if you have more than one derivative. So if you have a third order, then you have to actually evaluate, all the derivatives. You first calculate your your highest order derivative. You want to do your highest order derivative first, then you do the next one down and your next one down until you get to the main system. So you actually evaluate the one derivative and then you integrate, right? So if you have a third order system, you evaluate the third order derivative, then you integrate your this is a fourth order system here. I got a fourth order x4, or no, it's a third order. I define a variable x4, which is the third derivative, x3, which is the second derivative, and x2, which is the first derivative. So this is my equation here, but in this equation I have x, which is, like the position of the item, and then I have x2, which is the first derivative. And then I have x3, which is the second derivative. And then I have the third derivative, which I wrote it just as dx, d3x dt here. But notice here that this system is nonlinear because this last value here, this last value here is x to the third power. Okay, so it's x is to the third power. That makes it a nonlinear system. So when you plot that, you evaluate the third order derivative. So here's your third order derivative. And then the other values you simply integrate. So then now I've got my second order derivative, d squared x dt, is equal to the previous value of this plus my time step times the third derivative. Okay. And all I'm doing up here in the right-hand corner is doing a variable substitution. Okay, so you don't have to do the variable substitution, but sometimes it makes it a little easier to follow. Okay, once you do the substitution. But so then I'm going to do the first derivative is equal to the first derivative. That should be a k. Plus the time step times the second derivative. And then my final value, finally, x is simply equal to x of k minus 1 plus the time step times the first derivative. Okay. Now notice here when you do this, these derivative terms do not have to be vectors. Okay, so right now I've written these derivative terms as vectors. If you make them vectors, that's fine. You just have to make sure you initialize the first one outside of the loop. Or you can actually live without these if you don't want to plot them. Okay, so if you don't want to plot them, they don't actually have to be vectors. So you don't need the k minus 1 here unless you want to plot them. Okay, so if you don't want to plot them, then you can do that. If you just want to plot x and the first derivative, which is, and you want to plot that, then you can just do that one. So that one will have k minus 1, and then this one's k here. But the other ones can be scalars. So you just have to keep track and decide, do I want this to be a vector or do I want it to be a scalar? So if I made that one a vector, then I would have to make sure I just grab the one value of it. Okay, so you just have to decide how much of this you're going to keep. Now, if you want to plot all the different possibilities, then you definitely want to make all vectors. All right, so, but this week we're definitely going to get some interesting plots here. We're going to have some vector fields going on and some chaotic systems in our plots. The plots are definitely going to be a little more interesting this week. And like always, if you guys have any problems, make sure you contact me and I'll try to help.